The general trick to deal with logarithm integral functions. So again, here I have an integral involving Li function. If you don't know about Li function, Li is known as the logarithm integral function, and this is defined as integral from 0 to x of 1 by ln of t dt. Now, if there involves Li function, there's general trick that you can use to solve the problems. Because if you just leave it like this, just with the definition directly, it gets complicated most of the time. So a trick is to we introduce an integral representation in this way. I of a is equals to integral from 0 to x of e to the power minus a ln of t by ln of t dt. We introduce this integral instead of the definition. Now, with this integral, we manipulate, we make, we solve. Yeah, at last, we just find out the I of 0 because I of 0 is our current integral. Yeah, we are from 0 to x 1 by ln of t dt. So this will be our strategy that we will use in most of the problems involving L function and in the upcoming next videos as well and in this problem as well. So now let's see how this is useful. We can write this integral as integral, let's say I of a in the integral from 0 to x sine of a log x as it is. Yeah, sine of a log x as it is. And then a is already there. Let me just b over here. Let me just b over here. Yeah. Sine of a log x. Then this can be written as integral from 0 to 1 by x of e to the power minus b ln t by ln t dt. Yes, and also df. And our aim would be to just find I of 0. And that would be our required answer. Yeah? Yes. Now, okay. So what we can do is we can differentiate with respect to b now to simplify the equation because ln t comes down and we cancel out. So let us try to find ideas of b. Yeah. So it will be e to the power minus 2 ln t comes minus ln t, minus comes out. We have integral from 0 to 1 sine of a log x times. Now this is integral from 0 to x e to the power minus b ln t times minus ln t, minus is already here, times ln t by ln t dt dx. Yeah, and ln t cancels out. Okay, now next is, now we will have ideas of b is equals to, this is, now for this thing, we can just integrate this. Now it will be easy to integrate. Let's see if it's easily integrable or not. Integral from 0 to 1 sine of a log x. Yeah. And then this is just t to the power minus b. Yeah. So our integral will be t to the power minus b plus 1 by minus b plus 1. This is going from 0 to 1 by x and then dx. Okay. So we have ideas of b is equals to negative of the integral from 0 to 1 sine of a log x. And we can also write 1 by, okay, wait, there seems to be some major problem. Yeah, okay, it's solved. Now 1 by 1 minus b. Yeah, and over here, we know that this is x to the power minus 1. So this will be x to the power minus 1 means x to the power b minus 1 minus, now it's 0, it's 0. Yeah, and then dx. Yes. So are we doing good direction right now? Yeah, probably, yeah. Now, after this, we have I dash of b is equals to minus 1 by 1 minus b integral from 0 to 1 x to the power b minus 1 sine of a log x. Yeah? Yes. Now the next step that we will follow is we will try to simplify this expression by assuming log x is 1. So also note that if you just make this log x, it will become infinity to 0. Yes. So as to make it from infinity to 0, we can make a substitution y is equals to minus log x. That will just convert the negative infinity to positive infinity. Yeah. So we get I answer b is equals to minus 1 by 1 minus b. This is from infinity to 0 now. And x is just e to the power minus y. So e to the power minus y to the power b minus 1 means sine of a times minus y minus ay, and then dx will be minus e to the power minus y dy. Yes, yes. And now I dash of b will be minus 1 by 1 minus b. And now there are two negative signs over here that comes out of the sign and over here as well. These two will cancel out because this is an odd function. You can say that the negative sign of sine will just be outside, yeah, over here. And these two cancel each other out, yeah. And we can use the negative sign over here to reflect the limits of integral and make it go from 0 to infinity. Yes. And then we have e to the power minus yb plus y, and also over here minus y, which cancels each other out, and then sine of ay dy. Yeah. Now we see that we just need to use Laplace transform now. This is clearly an integral for Laplace transform, and Laplace transform is of sine a. Yeah. So we have e to the power minus yb sine of ay dy. And we know that the Laplace transform of sine x is just a by s square plus a square. Yeah. We use that formula, Laplace transform of sine x, which is 1 by 1 minus b. And over here, a by b square plus a square. This is s square plus a square. Yeah. So we are going in a pretty good direction. We just need to convert this to partial fractions. Now converting the partial fractions, since both just seem like constants, but actually b is a variable over here, the variable with respect to which we will just integrate. So let me replace b by x for some simplicity, so that it will be easier for us to understand. A by 1 minus x, and then x squared plus a squared. Okay, good. Now we have to finish the partial fractions. And we know how to finish the partial fractions. Just let it be equals to a by 1 minus x plus b by bx plus c by x squared plus a squared. Yes? Now, with the action over here, a x squared plus a squared, yes, and plus bx plus c 1 minus x. Yeah? Now, group the terms involving x squared, x is constant. So with x squared, we have a minus b. Yeah? With x, with x, we have over here b minus c. Yes? And with the constant, we have a squared and a square over here with the constant a square, and over here it's plus c. Yes, is that correct? Yeah, that's correct. Now by comparing the coefficients, x square with x square, x with x, and his constant, we see that a minus b is actually be 0 because there is no coefficient for x square over here. So we get a equals to b. Yeah. Similarly, b minus c is equals to 0. So we have b is equals to c. And over here we have a square plus c is equals to a. You know that c equals to b, b equals a, so we also have a equals to c. You can write over here a square plus a equals to a, so a is equals to a by a, a equals to a by a square plus 1, yeah. A by a square plus 1. Now if a is the same, b and c will also be the same, yeah. You can say that a equals to b equals to c equals to a by a square plus 1. This is the result that we have got. Yeah. Now, in this, we can now finally break into partial fractions. Since A and AB, all of them have same coefficient, we can just take that as common. Yeah, we can take A by A square plus 1 as common. And then we can write 1 by 1 minus x plus x plus 1 by x square plus A square. Yes. Now, if we integrate this with respect to x, we get I of x is equals to A by A square plus 1. Okay. And now this is just ln of 1 minus x by minus 1 plus, now this is 1 by 2 ln of x square plus A square, and then plus 1 by A tan inverse x by A. Yeah? Yes. And now it's also plus C. Now it's time to find the constant, but before that, let me just simplify these blocks into a single expression. I of x is equals to A by A square plus 1, and over here it's just ln of root under x square plus A square by 1 minus x. Yes? Yes. And then plus 1 by A tan inverse x by A, yeah, and plus C. Okay. Now to find the value of constant, we know that when x, that is b, if b goes to infinity over here, this will just go to 0. So overall integral will go to 0. Yes, so we know that integral will go to 0 when x goes to infinity. Yeah. So I of infinity will just be 0. And let's see what do we get from the other side. Okay. So ln of square root of infinity square root of infinity by infinity. Ln of 1, the ln of 1 is 0, plus 1 by a, which tan inverse infinity is pi by 2. So C. So we see that now this is just 0. This is just pi by 2 times 1 by a square plus 1. Plus C. That means C is equals to minus pi by 2 times a square plus 1. Yes, C minus pi by 2 times a square plus 1. Now, substituting this value, we will get the answer. Now, I of x will be a by a square plus 1, and ln of square root of x square plus a square by 1 minus x plus 1 by a tan inverse x by a, and c is minus 5 by 2 times a square plus 1. Okay, now this is what we have got. Now we just need to find out I of 0, because if c is 0, we get the required integral powers. So let's substitute x at 0. Let's substitute x at 0, we get I of infinity as, sorry, if we x at 0, we get I of 0, we get I of 0 as a by a square plus 1. Now this is just ln of a, x is 0. Yeah, so this is just ln of a by 1. So it doesn't matter, it's a. If x is 0, the a square is a plus 1 by a tan inverse 1 by a minus pi by 2 times a square plus 1. Yes. Okay, now we are almost at the end of the solution. Now just let us make some rearrangement to make this look proper. Yeah, we will have the answer then. So 1 by a square plus 1. This is a ln of a. Yeah, and this is plus tan inverse 1 by a. Okay, and wait. Oh, this is actually going to 0, not 1. If it's 0, tan inverse 0 is just 0. I think the error is understood. This is just be zero and just do not have no I mean the error is zero. That is just a zero. Sorry for the plain error. This is just a zero. So good now. And this is the expression. Yeah. And okay, so this is we get this over here now. I have to take one by s from common now. Here we get minus 5 x. Yes. And this is finally the answer that we are seeking for the now. Yes, it was pretty long, but it was pretty simple to be honest. It's just in the partial fractions and the trick that involves logarithm integral function. Yeah. So just recap, we use this trick that I told you earlier, and then we did differentiation on the integral sign. It's just Riemann technique that clearly simplified the integral, and then it was just power rule integral, and then we got a Laplace transform of sine a x a by x square plus a square. After that, we had to partial fractions, we decompose it, and then it was just high school integration ideas, and we evaluated it infinity to find constant, and we found out IF0, which was our required answer. That's how we solved this integral. Hope you enjoyed the problem. Thanks for watching, and look forward to seeing you in the upcoming videos.